All right, so we're continuing with the fundamental theorem of calculus and applications of the net change theorem, which we talked about in the last video. It has to do with the net change in the area. All right, so these are going to be applications where we're going to do that. So we're going to solve these graphically, where we'll be finding the areas graphically. All right, so we're given the monthly marginal profit, which, remember, marginal profit is the derivative. And so that's our marginal profit derivative of profit function in dollars per electric oven. All right, so we're going to do this graphically, and we're going to all do this on the calculator. So I'm going to graph my derivative. And they gave me, this is my domain. All right, and I'm actually going to use this when I go to graph. All right, label your axes and your intercept, and when I come back to graph it, I'll do that. All right, so I'm going to pop up my graphing calculator. All right, which I've already typed in my equation, but I'm going to double check and make sure it's the right, make sure I've typed it in right. Negative 0.03x squared plus 9x plus 500, so it looks like it's typed in correctly. All right, now before I go to graph, I'm going to go to window, right? The domain is the x values. Well, they told me they wanted to graph it over 0, so 0 is good, but up to 400. All right, so I'm going to change my x min to 0, my x max to 400. And then if I do a zoom fit, all right, so fit would be if I scroll down, right, so I have to scroll down to zoom fit, it'll graph the function over the domain. So there's the nice graph of my function over the domain 0 to 400. All right, so now I'm going to go graph it. All right, so our derivative function, which this is the x value, which is electric ovens. This would be the derivative, which is in dollars per oven, electric oven. All right, mark off my y-intercept because that's my starting point at time 0. When I plug 0 in, that starting point's up here at 500. All right, then if you remember from the calculator, it went up, and then it did eventually cross it later on down here, right? So there's the derivative graphed, all right, over the domain that they gave me. All right, there's my labels and everything. All right, so then I know my x values are in electric ovens. I know that my derivative is in dollars per oven. And so my area is going to be dollars in profit. That's what my area is going to be. All right, so they asked you to shade the region in the graph that represents the integral from 200 to 300 on my derivative, and what does this area find? All right, interpret it. All right, and so just so that I get it marked off, and then I'm actually going to find it on my calculator. I'm actually going to answer both of these together. I'm going to shade the region in on my calculator. I'm going to find it, and then I'll explain what it means. So I'm going to kind of answer B and C in tandem. All right, so I'm going to go back to my calculator. All right, going to remember, use the second trace, pick 7. All right, my integral function. We're integrating from 200 to 300. All right, and so there's the, so I can, when I go to graph it, it should be accurate. So there's the area from 200 to 300, and it's 85,000. All right, so go back to my function, shade it in. So again, my 200 was about right here, label it. 300 was about there. There is my area, shade it in. All right. And then explain what that value represents. Well, that area finds the net change in profit, right? That's what it finds. All right, this gives me the area finds the net change in profit when sales of electric ovens increase from 200 to 300, right? That's the from A to B, right? 200 to 300. That specific 100s, not any 100. So if I went to 250 to 350, I'd get a different answer. If I went from 150 to 250, I'd get a different answer. This specific change, if I increase sales from 200 electric ovens sold to 300 electric ovens sold, this area would find the net gain or loss in profit. Well, we know what it is. Right, that came out to 85,000, and so we have a net gain. Right, that's what that area would be in profit. Of 85,000. All right, and so when they sell that 100, going from 200 to 300, they're going to gain a total profit of 85,000. This means they get $85,000 in profit at 300. No, that's not what that means. It means that's the change in profit when I go from selling 200 to 300. All right, that's what that means. So that's the change, right? The net change in profit from the sales of 200 to 300 ovens. All right, that's the net change. It's exactly how much additional profit they get when they sell that 100 units, 200 to 300. All right, next example. Marginal function now with cost. All right, so a marginal cost function. All right, so we're given the derivative of the cost, which is our marginal cost function, in dollars per item, dollars per unit. They also tell us the fixed cost. So again, the fixed cost would mean that would be my constant. That would be the C value would be 7,800, or if we don't produce any, right, that's the initial value. All right, 0 items are produced. 700 is still my cost. It's fixed. And no matter whether I produce 0 or 100, that's the tacked on cost. So this might come into play when we have to answer one of our questions later on. So I'm going to keep that in mind in a little bit. We'll answer A first. All right, find the change in the cost of production is raised from 200 to 210. All right, so I want to know how much additional cost those 10 units are going to cost me. And it's specifically the 10 units from 200 to 210. If I went from 190 to 200, that'd be a different 10 units. And so I want to find this change. All right, exactly what this change is. Well, that would be integrating from 200 to 210 of my derivative. All right, and again, I'm going to do this graphically. All right, so I'm going to go to my function. So again, I've got mine in there. I'm going to go here, clear that one out. I don't need it anymore. And then it's this one. I'm going to double check and make sure I've typed it in there correctly. So 0.03x squared, negative 2.5x, and then plus 150. All right, looks like it's good. All right, again, I'm going to change my window. I probably don't need quite as big of window. Maybe I'll start with that window. Perfectly fine window. All right, good enough. All right. And so I want to find, so there's my derivative of my cost function. All right, so that's the cost. And then I'm going to find my area from, I've forgotten what my numbers were, 200 to 210. All right, so I'm going to integrate from 200 to 210. So second trace, 7. My lower limit's 200. My upper limit's 210. All right, we'll shade in. That's that little bit of area. And so 8,985. 8,985 is the change in cost to produce those 10 units. So again, they'll have a increase in cost of exactly $8,985 if production is raised from 200 to 210. And again, it's important that it's 200 to 210. If I picked a different 10, right, it's those 10 units. If I picked a different 10 units, I'd probably get a different change in cost. All right, so that's how much it costs for those specific 10 items. All right, find the cost of producing 210 units. Alright, so B is asking me to find cost at 210. Alright, this is where that first piece of information is going to come into play. Alright, I know the cost to produce 0 items, and you can do this as the initial value problem like we did in the earlier sections if you want to, but I'm going to use my fundamental theorem of calculus. Alright, I know we were given the fixed cost, so the cost to produce 0 items was 7,800. Well, if I can find the change in cost from going from 0 to 210, I can find how much it cost me at 210 because I just add that to my 7,800. Alright, so I'm going to find the change in cost. Alright, well, using my integral going 0 to 210 of my derivative of my cost, which I've already got graphed. I know that's 7,800, right? That's what that is. I just input it in there. And so if I find out what this is, I just have to add that 7,800 to the other side, and I'll get what my cost is. Well, I can find this on my calculator. So I'm going to go back to my calculator. I don't have to change anything, right? If you don't like that little bit of area there, you could regraph it if you want to. I'm not. Alright, now I want to find the area from 0 to 210, so all of this area. So I'm going to hit second trace 7. Integrate from 0 now to 210. Ooh, I have too many zeros. Delete. There we go. Enter. There we go. Alright, now it'll shade it in. Alright, so that's what a cost is for 210 items. Alright, that's how much the 210, the increase in cost. That's the net change from producing 0 to 210 items. Alright, oops, I already forgot what it was. 68,985. So 68,985, which is how much more it costs me to produce 210 items than nothing. Then I do have to tack on this fixed cost. Right? Because that's how much it costs me whether I produce 0 or all of them. I always have to tack that on. So 210 actually cost me $76,785. That's the cost to produce 210 items. Exactly. And I didn't have to find the cost equation, although I could have. You could have done this as an initial value problem. Alright, the last one. Sketch the graph of the marginal cost function, shading the area that answered part A, which we already had that before. So that was this one, so shading that in. So I'm going to erase this part B and draw it here. So that was that first one we found. So I'm going to try to do it from memory. Probably should eventually switch the questions here, but well, since this is the way I set it up, this is the way I'll answer it. Alright, so remember what we found on the first one. So our items, dollars per item, right, the derivative of the cost. Alright, there's the derivative of the cost. And remember, the 210 was just a little strip of area right there. That was again, the first part that we did. If you go back and look at the first part, 200 to 210, that area was that 8,985. Alright, which equaled that net change from 2000 to 2010 of our derivative. Right, that was the answer to part A. Alright, make sure I answer the question. Sketch the marginal cost, shading the area that answered part A. Alright, so there's my marginal cost with my everything labeled correctly, and there's the area that we found and answered part A with. Alright, the next question. A glass of juice at room temperature, 66 degrees Fahrenheit, is placed in a refrigerator at 1 p.m., so that's times 0. So as soon as it's placed in the refrigerator, and then it cools off, right? That's what the refrigerator does. It cools things down. We know how fast this particular juice cools in a refrigerator. Alright, X hours after it's been placed into the refrigerator, it's changing at a rate of, so again, that's my derivative. That's how fast the temperature's dropping when the juice has been placed in the refrigerator. For the first 10 hours. Alright, I'm assuming after 10 hours it's leveled off and it's as cool as it's going to get. Alright, show all your work, including any integral used. This is typically how I ask the question on the test. Alright, we want to know how much will the temperature of the glass drop, change from 1 p.m. to 5 p.m., the exact change in the temperature. Alright, so make sure you're careful. One of the hard parts about this question that students will miss is 1 p.m. is time 0. X represents the hours after you've placed it into the refrigerator, which would be 4 hours. It's been in the refrigerator for 4 hours. We want to know how much the temperature of the juice changed over the first 4 hours it's been placed in the refrigerator, right? A lot of times students will want to use 1 and 5, and that would be different. That would be the first hour to the 5th hour. Right? We want to know that. We want to know from the 0, when it's been placed in there, to 4 hours later. How much did the temperature change? All right, so the exact change in temperature over the first 4 hours, that's what that represents. Change in temperature from time 0 to time 4 is integrating my function from 0 to 4, my derivative, my rate of change in temperature. All right, which again, we'll do this graphically. All right, so since we've done a few of them already on the calculator, we graph this. Again, you might want to adjust your window a little bit. You might want to fit it over this domain, right? 0 to 10 is the domain given, so you'd type that in and you'd fit it. All right, so when you type that out and you sketch it on your graph, it should look, all right, this is the axes. Oops, forgot my x-axis. And so this is what the graph of the derivative looks like if you graphed it using the domain. So it's all below the x-axis, right? There's my x-axis, there's my y-axis. This would be the hours, and the y-axis would be the temperature per hour, right? The drop in the temperature per hour. All right, and then we find our area from 0 to 4, all right, and it would shade it in. It would come out negative. That value should come out negative on your calculator. All right, it's below the x-axis, so it's a loss, right? And it should make sense it's a not loss. It comes out 3.14985, so I'm just going to round to 3.5. All right, so that means this equals negative 3.31.5, and so the temperature of the juice dropped by 31.5 degrees Fahrenheit in the first 4 hours. All right, now that's not what the temperature of the glass is, just an FY. I didn't ask this in the question, so that's how much, that was the answer to the question. It's change in temperature. We put it in there. It was 66 degrees Fahrenheit when we put it in there. The temperature cools it off, and this is exactly how much it cooled it off by. And so that was the answer to the question. The temperature dropped by 31.5 degrees Fahrenheit. So the second part of this, just a kind of an FYI, a note. What is the temperature of the juice now? At 5 p.m. All right. Well, it was 66 degrees Fahrenheit at 1 p.m. It was placed in the refrigerator, and it dropped by 31.5 degrees by 5 p.m., which means we take our 66, subtract our 31.5, and that's how much the temperature of the juice dropped, right? And so it is now at 34.5 degrees. All right, that's its current temperature. I guess at 5 p.m. Right, again, didn't ask it, but that's just a kind of a neat thing you can figure out. All right, the last question for the set of notes. All right, so book problem number 70. Suppose that we're given the rate of change function that finds the rate at which we memorize words per minute. All right, so if you're memorizing words, all right, vocab words or something, this is how fast that, I'm assuming is based on averages, that you memorize words per minute. This is the speed at which you memorize, particularly words. All right, use that figure to figure out how many words can be memorized in the first 10 minutes and then the second 10 minutes. So they're asking two questions. All right, so the first question is we want to know in the first 10 minutes how many words are memorized. You can read that. So it'd be the net change in how many memorized from time 0, where you don't have any memorized, over the first 10 minutes. Alright, so we'd integrate from 0 to 10 of our derivative equation. Alright, which again, you can solve this graphically, or you can solve it by hand. You could actually solve it either way, I don't care. Alright, so by hand or graphically, most students will solve it graphically, so that's what I'm going to do. Alright, so you graph this function in the calculator and you shade the area from 0 to 10. Alright, so if you graph it, now you might want to make your window a little bigger because I know I'm going to go out to 20, so I might graph it if I were graphing this function over 0 to 20 would be what I'd set my domain. Alright, so it's going up like this when I graph it in there, and so starting 0 to 10. We'll shade this area in. Alright, so 0 to 10 comes out. Nine words memorized. Nice exact number, right? That area is exactly 9. So 9 words memorized. Alright, well the second 10, so now we'd be looking at up to 20, so we're looking at this area. So I don't want this anymore. And so the second question, now we'll use the same graph. So question number 2, the second 10 minutes. So the second 10 minutes, which means from 10 minutes to 20 minutes, how many words are memorized. Alright, so I'm memorizing between 20 and 10. That's the net change I'm looking for over that specific 10. So it's a different 10, right, which means I should get a different answer, right? It's a different area. So I'm memorizing from 10 minutes to 20 minutes. So it's 10 minutes, but it's the second set of 10 minutes. Right, from the same equation, so the same m prime of t that we've got graphed here, m prime of t, but now it's this area that we're finding, which should give me a different number of words. So again, use the same graph I had before, but now my lower limit's 10, my upper limit's 20, and so it's going to shade 10 to 20 in that second area, and I can memorize more words because I must be in a groove, right? We're already, our brain's revved and going. And so we learn much more in the second set of 10 minutes, right? We've got 23 words were memorized. So altogether it would be 31, right? Over the total 20 minutes, we'd learn 32 words. Add 9 and 23, it would be 32. 9 of them were memorized in the first 10. 23 were memorized in the from 10 minutes 20 minutes. Alright, then we will stop there. Alright, so we will continue on, but next applications we're going to look at are specific to distance, velocity, and acceleration. So we're going to look at physical science. Kind of the same idea, so remember the derivative of distance is velocity, derivatives of velocity is acceleration, and the applications of those. And that will wrap up this section.